In recent years, the decline of natural pollinators has become a growing concern for agricultural productivity, particularly in high-value crops such as avocado. This situation has motivated increasing interest in technological approaches that can support or complement traditional pollination process through autonomous and intelligent systems. This work was developed by a collaborative academic team. My name is José Ortiz, affiliated with the Corporación Universitaria Minuto de Dios. I co-authored this research with Oscar Loyola-Valenzuela from the Universidad de las Américas and Cristian Alexander RINCÓN GUIO, also from the Corporación Universitaria Minuto de Dios. Based on this context, to date I will present our work entitled Agricultural Pollination Innovation, a theoretical analysis of the potential use of robotic bees for avocado cultivation in Colombia. Pollination is a fundamental biological process that directly affects agricultural productivity. However, over the last decades, natural pollinator populations have declined significantly due to pesticides, habitat loss, and climate change. According to FAO reports, more than 75% of the global food groups depend at least partially on pollinators. Avocado is a particularly sensitive crop as it strongly depends on cross-pollination. In countries like Colombia, where avocado production is rapidly expanding, this situation represents a critical risk. These challenges motivate exploration of technological alternatives that can complement natural pollinators in an scalable and controllable way. To evaluate this strategy, we modeled a avocado orchard as two-dimensional grid of trees. Flowers are distributed stochastically around each tree and exhibit temporal reproductivity, following the A and B flowering phases characteristic of avocado crops. Drones are modeled as autonomous agents with kinematic constraints operating under simplified motion dynamics. Energy consumption is assumed to be proportional to the traveled distance, which provides a reasonable approximation for small agricultural drones and allow us to focus on coordination effects. We compare it to heuristic coordination strategy. We employed a factorial experimental design to ensure a fair comparison. The simulation considered different swarm sizes ranging from 3 to 10 drones and different flowers densities per tree. Each configuration was repeated multiple times with independent random seeds, resulting in a total of 70-20 simulation runs. We evaluate performance using 4 metrics: final coverage, time to reach 90% coverage, energy efficiency, and workload imbalance among drones. When analyzing energy consumption, the greedy strategy requires less energy per effective visit, particularly in sparse scenarios, due to shorter travel paths. In contrast, the sweep strategy incurred a higher energy cost but maintained a much more balanced workload among drones. The greedy strategy Taken together, these results show that no single strategy dominates across all the performance metrics. The sweep strategy is more suitable when robustness, spatial completeness, and fairness are critical, while the greedy strategy is advantageous in energy-constrained or exploration missions. In conclusion, this work provides a quantitative and reproducible comparison of coordination strategies for multi-drone pollination. Our results indicate that suite-based coordination offers higher reliability, while greedy coordination improves energy efficiency and the cost of imbalance. As future work, we plan to explore hybrid and learning-based strategies, incorporate more realistic constraints such as communication delay, and validate the model using small-scale experimental prototypes. Ultimately, this is the reference used in this presentation, and thank you for your attention.